Howdy folks, welcome back to another CS 128 honors lesson. Today we'll be discussing the ideas of ownership, and that's pretty much it. So without further ado, we'll go ahead and get started. So, as I briefly mentioned, the goals for today are to introduce this idea of ownership. But some quick reminders, don't forget about homework 1. Let me bring my camera up. Okay, don't forget homework 1 is due tonight. Homework 2 is due Thursday, and MP0 is due Friday. Homework 3 should be releasing tonight, and we'll start to introduce you to some of these ideas of ownership as well. So that'll be due a week from now. That's pretty much it. If you need extensions on any of these, please feel free to reach out. Yeah. But first, we had some good responses from the feedback form on the first homework. So this is from homework 1. And so here's some quick ones that I wanted to briefly discuss. So first, a pun. What's the object-oriented way to become wealthy? Inheritance? Okay, I don't have any little drum roll like da-da-tss, but okay, good one there. That was pretty good. I give this one a 7 out of 10. So what's the difference between the underscore keyword and the other keyword in the match statement? When should I use one over the other? Okay, this one is a little bit more complex. So say we have some match statement and we have some cases, and then eventually we want to match, basically anything else. Okay? And the question is, which do we do, other or underscore? Okay, there is a difference between the two. So underscore is sort of this, I can't remember that. I think it's called a reserved keyword or reserved wildcard in Rust. It does different things depending on what it's used for, but in this situation, this is what we call a pattern. When the underscore is being used as a pattern, it's a wildcard pattern. And so it will match anything, or rather the pattern will always match is a way you can think about it. But this variable underscore will not be passed towards the end here. So if you wanted to try to print, I won't write it out with my mouse handwriting, but if you wanted to do like println underscore, that wouldn't be possible because this underscore is not able to be used as a variable. However, if you use the other keyword, I think generally speaking, this will match anything that is not none. I'm not quite sure if it will match none or not. Someone might have to test that, but it will match something and then assign the thing that it matched to the variable called other. And so you could, for example, println other here. Okay, and then it would print whatever it matched, and of course many things can match with a single variable. A tuple can match with a single variable because, we can say like let x equal some tuple. An int, a float, a string reference. There are, I'm sure, some things that don't, but I can't think of anything off the top of my head. I'm sure this gets into some more complexity when we bring ownership into the mix here, which we'll learn about very soon. But in general, if you want to match anything, use the underscore keyword, because I'm sure there's edge cases in the other case. Okay, low key, let me get to that one next. Do we get to see model answers for the homework and MP after the deadline? I don't think I did the homework efficiently, but I got full points, so I want to know how to fix it. Okay, for MPs, the answer is yes. We're going to have that be a relatively large part of lecture, the lecture after MPs are due, where we'll sort of walk through common pitfalls, good approaches, things like this. So absolutely. For homeworks, we weren't considering it. There's a relatively high number of homeworks, I think like 13 or 14. One every lecture, basically. We're happy to release code to sort of give you references on how to do it, but we probably will not discuss it in lecture. So I'll say MPs definitely, homeworks maybe. Let me know in the Discord if there is an interest in seeing homework solutions, and we'll. I think we have some GitHub that we can throw them on. Okay, before I forget, I'll get to this in just a moment, but before I forget, there are some updates with our website. Specifically, we have the calendar. Let me see if I can bring this up. In the meantime, you can watch the quad. Okay, which tab is this? Is it this tab? Yeah, okay, it is this tab. So let's bring this up. How's the quad looking in the meantime? Okay. So here's our website, honors.cs128.org. What a URL, I know. And there are 2 additions in the meantime. First, there's the schedule tab, which discusses every single lecture in MP from now until the end of forever. And so if you ever want to reference when things will be due, this is your number one thing, as well as it discusses topics. This is subject to change, so we might move things around, but it's pretty locked in. There's some things that will still move. I think, week 9, we have some empty lectures that we're debating having some interesting topics for. So, okay, second, Hall of Fame. This is last semester, so these are the sort of most impressive projects that we saw from last semester, the final projects. So if you do want some inspiration, then you can look here for that. So ray tracers was Harry, as well as many others. Harry is actually now on staff, which is why I'll single him out a little bit here. But if you all want to, you can open up their files and you can sort of explore the different things that they did, right? So I think that this group, obviously, as the name suggests, did a ray tracer in Rust. We're going to add some pictures and videos to these as well, so that you'll actually be able to see them. I think, obviously, ray tracers in specific, that'll be pretty exciting to see. Okay, back to the quad cam. And then back to lecture. Look at that. Okay, finally, Loki, Wish, Pray to Learn gave compilation stuff. So we actually don't really want y'all writing code in Pray to Learn. We really would prefer you to write this locally. And then to upload the code to Pray to Learn. There was another message that said, we wish that we could just upload the files. We'll look into that. If it's not too hard, then we'll see if there's a way where you can just upload the files rather than copy and pasting the code, since it is a little annoying. But we really would prefer you to develop locally. There's 3 major options for this. One, there's the Rust Playground, which is an online IDE. That's very useful for just testing functions, short snippets. It's not as good when you have multiple files, so don't use this for your final project. If you use it for homeworks, that's totally fine. MPs, you might have to download the actual files. The second option is obviously using it in your Vagrant VM. So we provide you with the files. There was this issue with this week 1 crate. We're gonna fix that. That won't happen again. Sorry about that. So there should be no more issues with that local files from this point on. This next option is using it in your Vagrant VM. We've already installed Rust for you. It's the same version of Rust that we use, so there shouldn't be any issues here. And then the third option is Rust locally. So, obviously nothing is stopping you from going to the Rust website and downloading Rust and running it locally, not using your Vagrant VM. This is fine. We actually maybe recommend this for your final projects. It's effectively the same as using your Vagrant VM, but it's a little bit easier to actually get the files into there. So, it shouldn't be too hard. But anyway, all of these are great options, and we'll make sure that the compilation issues that you see will be shown to you quickly rather than very slowly through Pray to Learn. Okay, so without further ado, which I already said, we'll go ahead and get started. And really this idea of ownership is Rust's way of dealing with managing memory. And there's a couple different ways of dealing with managing memory. First, there's this idea of garbage collection, which a lot of languages do in the past. Lisp, I believe, was the first. Now, many languages do it. JavaScript, Java, Python, tons. And the idea here is, we create we request some block of memory from the operating system or from your computer, and we fill this with the data that we want. And then occasionally, while your program is running, it will sort of inspect all of the things that it has provided you with and see if they're not in use, see if they're in use or not anymore. And if they're not in use, it can free up that space. Okay, this isn't perfect. Garbage collection can cause lots of inconsistencies in program speed. It can cause inconsistencies in what memory is available when. It has its own issues. Garbage collection isn't perfect. Mostly it's slow and it leaves a lot of space that isn't being used. And really that's a key point here is we want to free this space as soon as possible, but no sooner, right? Because we always want to make sure that we have as much space as possible to run our program or for other programs to run. Okay, so garbage collection isn't perfect, it's slow, it's inconsistent, etc., etc. The next way, maybe y'all have heard of malloc and, oh, whoops, spoilers. Okay. So the next way is to let the programmer worry about it. So this is you request when memory is allocated manually, and you also, tell it when to delete that memory. So, C, C++, many other languages require you to choose when you're allocating and deallocating memory. Clearly, this has its own issues. When we're working with these complicated data structures, okay, say we have like some linked list, right? All of these are things that we have to allocate space for because they have some data and they also have some pointer to the next neighbor. If we, changed this pointer like this, suddenly we've lost access to this data. Maybe I shouldn't use yellow. Suddenly we've lost access to this data. And so we have now a memory leak. And, if you've heard that term before, this is really where that comes from is it's hard to manage memory manually. We're not very good at this. And so, this also clearly has its own issues. And then Rust has its own solver. So Rust has ownership. And this is what we're going to be learning about today. And the big idea of ownership is whenever we're allocating some space, we're going to keep track of who's using it. And we can keep track of, if the person who's using this space, or I should say the variable who's using this space is no longer needed, then we also know the space is no longer needed, right? But because of these rules, there's some complexities that we'll face. And that's what we're going to be exploring in this lecture. Well, introducing in this lecture. Okay, ownership is a new concept. It can be confusing. And so our goal today is just to introduce it and to give you guys and gals a good idea on how, and non-binary folks, a good idea on how this works. So there's 3 major rules of ownership. First, each value in Rust has a variable called its owner. Okay? So if we say, for example, let x equal 5, this number 5 is the value, okay? This holds up some space in memory, and it has an owner, and that owner is the variable x. Second, there can only ever be one owner, okay? And so we'll look at some examples of this, but at the end of the day, if you have some piece of memory, there can only ever be one variable that's pointing towards it. And okay, there is some exceptions with multiple ownership, some more complexities that we'll learn about in the future. But to introduce this idea of ownership, keep these in mind. And really, these will take you pretty much as far as you need to go. So there can only ever be one owner. So every piece of memory has only one owner pointing to it. And then 3, when the owner goes out of scope, the value is dropped. Okay, so let's look at a code example. Okay, and let's recall how scope works. So we'll sort of artificially create a new level of scope with these curly braces here. We'll call this scope level 1, and we'll call this scope level 0. Okay? And so we can analyze at a couple different points the status of x. So obviously, anytime before we initialize x, x is not in scope because it's not initialized. The moment after we initialize x, x is initialized, and it is in scope, so right here. Meaning we have access to x, this lives somewhere in memory, etc., etc. We can use it, right? But once we leave scope, x is obviously no longer, we won't be able to use x. For example, if you call some function and that function creates some local variables and then returns, you can't use the local variables that function returns, or that the function used, unless the function returns those variables, right? And you then, kind of catch them. So obviously when things go out of scope, they can't be used. But this is a little bit more important because we also have to realize that when x goes out of scope, the value that x is pointing to is dropped. Okay? We no longer care about what's there. And this is the exact same with string literals. And it's similar, but there are some differences when it comes to capital S strings. And this is really the example that we'll be talking about today. You all have been exposed to this kind of complexity already, this capital S string versus string reference. And we're going to see why that complexity exists today and use it as an example. So let's analyze first with this idea of the stack and the heap. Okay, so I'm computer engineering, so apologies for those of you who don't like the hardware, but I think it's very important to sort of analyze what's happening at a low level to really understand why we need to do these things. So this is some piece of memory that we have on our computer. And the area that we want to pay attention to right now is this here. And you can think of this as the space that it's taking for our program to run. And there's other pieces, global variables, the program code itself, those might live over here or up here. But in the case of, when you call a function and when you allocate some object, those are all going to live here. Okay? And the two parts inside of this are called the stack and the heap. And both of these two things grow towards each other. The stack generally grows when you create local variables, when you call functions. Say a common example that y'all might have heard of is, okay, if you have some recursive function that calls itself, but you mess up and it calls itself infinitely, what'll happen is the stack will keep growing and growing and growing until it collides with the heap, and your program will crash, and the error that you will get is Stack Overflow, right? Which, okay, hopefully y'all are a little bit familiar with Stack Overflow. Similarly, if you keep allocating objects on the heap, it will grow and grow, and you'll get the heap overflow error, which is not a popular website, I don't think. Okay, so I mentioned how when you call a function, it grows the stack a little bit. And that's because this is what a function looks like on the stack. Now, a lot of these I'm not going to talk about. I think you talk about them in like 231 or something. That's outside of the scope of this class. But there are some important ones that I want to point out. Notably, parameters to a function, and really importantly, local variables. Okay, so in this example here on the right, we enter some scope, which means we build up what we call this stack frame. And, somewhere here, this x is stored as a local variable. Because that's what it is. It's a local variable, right? And so that takes up space, clearly, on the stack. But I want to draw a little bit of a distinction, which is when we instantiate objects that are not of constant size, vectors, capital S strings, things like this, and generally, larger things in general. Anything that you need to sort of point to rather than directly reference and copy, these are going to live on the heap. Okay, and this heap, just represents that it's a different part. Rather than directly sort of having access to this, we have a pointer. This local variable is the address, so we'll just say this lives at like x23f or something. Okay, and so the variable here is x23f. And in order to get this string hello, we first have to go here and then read what's there. Okay, and this is very powerful because it allows us to adjust the space, right? We allocate some little piece of space here and we say hello. And then we can very easily sort of make it bigger if we need to, or, reallocate a bigger space and copy it over if we absolutely have to. And compare this with local variables. If hello is here and all of this other stuff is above it, you have to move all of these before you can make this bigger, and that's really expensive and slow, and so that's why we have this sort of distinction. Okay, so local variables are stored on the stack, instantiated objects and larger things are stored on the heap. So when we return from some function, which you can say is the same as going out of scope, remember rule number 3, we tear down the stack. Because, for example, we no longer need these local variables, right? You call some function, it uses local variables, we return from the function, we don't need those local variables anymore, okay? Unless we return them, but that's a different process that I won't go over. Okay, and so the important kind of part here is we're also going to say, hey, this local variable here is pointing towards some address in the heap. And if we no longer need this local variable, because of these ideas of ownership, there can only be one owner, meaning this is the only thing pointing to that. We know that we no longer need this space in memory. And that's it. That's really the heart of ownership. It's just tying together these ideas of when you go out of scope, knowing that you can also delete this space on the heap. Of course, these rules that we've introduced earlier, every single piece of data on the heap has to have an owner, meaning it has to be represented somewhere here. that owner is the only owner, meaning, for example, what if there were two that both pointed towards this? Okay, well, we drop local variable 2, and so we clear this piece of data, and then we drop local variable 1, and we clear this piece of data again. But we can't do that. That's not ours to clear, right? That's an illegal sort of operation, and your computer can explode, which is bad. We don't like it when computers explode. We try to avoid that usually. Okay, and then the third rule is, what was the third rule? There can only be one owner. And then when the owner goes out of scope, of course, the value is dropped. Okay, and that's really it. So that allows us to kind of fully manage the heap and data on the heap. Okay, so let's get a little bit more complex here. So what's happening in this example? So we create some local variable with the value 5. We copy that data into some local variable with the value 5. And then we change this value to 6. Okay, clearly from our intuition from programming, what's not going to happen here is this is also going to change to 6. Okay? And this is because these local variables do behave a little bit differently than variables in the heap. Okay, and we'll see the same example with data on the heap in just a moment. But what happens when we're working with these local variables, data on the stack, is these basic types, and we'll look at this in a moment more deeply, implement this thing called the copy trait, which is anytime you sort of do this little interaction here, rather than transferring ownership, which we'll look at, we're copying the data over. Okay, and so these do represent two distinct sort of locations. But this isn't the same. So what's going to happen here? And really there's two options, okay? We remember in the local variable case, we have this, and then we copy this data over to here, and then we can change this, okay? And so that's a little bit like this example, maybe, right? This local variable, S1, looks exactly like this. It has 3 fields, pointer, length, and capacity. Pointer representing where in the heap this data is, length representing how many characters it is, and then capacity representing how much extra space we have before we need to kind of get more space. Okay, and so what if we just directly copy these things, like in this first example on the left? Great, okay, now we have both S1 and S2 pointing towards this location. But this is clearly a problem, right? We've already violated one of the laws of ownership, which is every value must only have one owner, right? And so what'll happen, if this was the case, was, okay, we drop S1 because S1 goes out of scope, meaning we free this data, and then we drop S2, and then we free this data a second time. But that data isn't ours to free. That data might already be being used by a different program, right? Okay, so clearly this left side can't be the case, so it must be this right side, right? Well, the right side's also not really correct, because first of all, what if we want these two things to be representing the same piece of data, right? What if this, data here is something that S1 needs to change, and then when we read from S2, it also needs to be changed? Or, I mean, an even easier example is what if this isn't the last level, right? What if this is a pointer to some array, and this is a pointer to some different array? This is a pointer to some different array. And then if we just copy, this level, we're pointing to the same arrays in the end. And so it actually doesn't really accomplish anything. Okay, we can keep going deeper and deeper and copy all of those, but then this copy becomes extremely expensive, and it still might not do what we want, because we still might want these to represent the same piece of information. Okay, this is what we call a shallow copy. This is what we call a deep copy. And there's times when both of these are important, but neither of them do what we want them to do. And with the rules of ownership, neither of them work. And so we can't do that. We can do a third option, which is what we'll do is S1 is no longer valid. We've transferred ownership from this location in memory from S1 into S2. So S1 no longer has permission to interact with this data. Okay? And so let's look at what that looks like. So what happens if we try to interact with it anyway? Well, we get this error. So, and this is one of the reasons why Rust is so great, is this error is very easy to read. So borrow of moved value S1. So we're attempting to borrow, which we'll talk about in the future, some value that has already been moved. We've moved ownership over. On line 4, the move occurs because S1 has type string, which does not implement the copy trait. This is saying, hey, I don't know how you want me to copy this object, right? If this was let x equal 5, let y equal x, this is easy to copy. I know how to copy a 5, but I don't know how to copy a string. Do you want to do a shallow copy? Do you want to do a deep copy? I don't know, right? The Rust compiler doesn't know, and hence the error sort of occurs. And, because I don't know how to do this copy, my only option is to move the value, which occurs here. So we've moved ownership from S1 into S2. And then you've attempted to use this value after the move, which is not allowed. And thus the error occurs. Borrow of moved value, borrow after move, right? And so that's really the core idea of ownership. And that's really it. There's some extra complexity which comes into account. So you'll discuss borrowing, basically the idea of, okay, we can say, can I just use this for a little bit and then give it back? And the answer is yes. And we can, sort of be a little bit more active with how we're letting things own different things. So, we can keep track of who's owning this a little bit more actively and choose where it should go. And we'll look at a ton of examples of that over the next 2 lectures, I believe. So you do, of course, though, have options, right? You're not sort of stuck only ever having one thing. If you do need to clone this data, you can clone the data using the clone trait, which is similar to the copy trait, but is a little bit deeper, right? This performs a deep copy rather than a shallow copy. If you need to perform a shallow copy, you'll learn of ways to do this in the future, but that's I think gets into the territory of unsafe Rust, because we've talked about, if you do a shallow copy, you now have 2 things pointing towards the same location and things might explode. So we'll maybe discuss unsafe Rust in some special lectures in the future, but this is something that we might not want to talk about yet. Okay, that's pretty much it for ownership. If y'all have any questions, I really encourage you to ask so in the Discord. We're here to help. Ownership can be a little bit complex. One other point that I want to sort of briefly mention is it can be a little bit difficult sometimes to keep track of what has and does not have this copy trait, right? I mean, it sort of felt natural that we can just copy this here. And the answer is maybe what you'd expect, which is anything that lives on the stack is going to implement this copy trait. So, ints, floats, chars, booleans, right? All of these sort of basic types that are going to take up some fixed space in memory. Maybe more interestingly, things like string references implement the copy trait. I believe arrays implement the copy trait. Arrays and tuples implement the copy trait depending on what's actually inside of them. Obviously, if you have a tuple of a capital S string, and then, I don't know, anything, we can't copy this tuple because we run into the same issue, right? We'll have 2 pieces kind of pointing towards the same location. And so if the string contains things that implement the copy trait, if the tuple contains things that implement the copy trait, then the tuple implements the copy trait as well. So keep track of these things. It can be a little bit complex, but at the end of the day, it should feel pretty natural. Things that fit on the stack that are small, fixed size, that we know the size of, are able to be copied and are also quick to use, right? Okay, that's pretty much it. I hope you all have a wonderful rest of your week, and